Taipei 101 has a 660-ton gold steel sphere hanging inside it, suspended by cables between the 87th and 92nd floors, visible to tourists through a viewing window. It isn't decoration. It's the single piece of engineering keeping the building livable in high wind. Tall buildings don't just need to resist wind without collapsing. They need to resist swaying enough that people inside can function. A skyscraper flexing even a meter at the top during a storm won't fall down. Modern structural engineering handles that easily. But occupants near the top will feel seasick, furniture can shift, and elevators can jam in their shafts. Wind doesn't push steadily either. It arrives in gusts, and it also sheds vortices, swirling pockets of turbulence that peel off alternating sides of a tall building and create a rhythmic side-to-side push. If that rhythm happens to match the building's own natural sway frequency, the motion amplifies. The same way pushing a swing at exactly the right moment sends it higher with very little effort. Uncontrolled, that resonance is the real comfort and safety problem tall buildings face. A tuned mass damper solves this by putting a second, independent mass inside the building, mounted on springs or cables so it can swing on its own. Engineers calculate that mass and its suspension system, so its natural oscillation frequency closely matches the building's own sway frequency. When wind starts pushing the tower one direction, the damper mass, because of its own momentum and tuning, ends up moving in the opposite direction at nearly the same moment. That countermotion physically pulls back against the building's sway. A viscous damping element, essentially a controlled friction or hydraulic resistance system, then converts the kinetic energy of that swinging mass into heat, bleeding off the energy that would otherwise keep feeding the building's oscillation. The building doesn't stop moving entirely. It moves noticeably less, and critically, it stops accumulating energy into a dangerous resonant sway. Taipei 101's damper is one of the largest and most visible examples in the world. The 660-ton steel sphere, 5.5 meters across, hangs from the 92nd floor down through several stories on thick steel cables, essentially acting as a giant pendulum. Below it sit hydraulic pistons that provide the viscous damping, absorbing energy as the sphere swings. During Taiwan's frequent typhoons and earthquakes, the sphere visibly swings several feet inside its housing, and that visible motion is proof the system is doing exactly its job, moving so the building doesn't have to. Taipei 101 was completed in 2004 specifically to survive both extreme wind and seismic activity in one of the most disaster-prone regions for tall buildings on the planet, and the damper was central to making that possible. A suspended pendulum sphere is only one design approach. Some buildings instead use a tuned mass damper that sits on a sliding or rolling platform, with springs pulling it back towards center rather than gravity alone. Others use liquid dampers, essentially large tanks of water or specialized fluid, engineered so the fluid's own sloshing frequency matches the building's sway, dissipating energy through fluid friction and turbulence instead of a solid mass. The choice depends on the building's specific shape, height, and dominant sway frequency, along with cost and available floor space. Since a damper this large has to occupy real usable square footage near the top of an extremely expensive building. Whichever form it takes, the underlying physics is identical. A secondary mass tuned to counteract the primary structure's motion. Getting the tuning right is a genuinely difficult engineering problem, not a rough estimate. Engineers have to calculate the building's natural sway frequency using detailed structural models and wind tunnel data long before construction finishes. Then design a damper mass, spring stiffness, and cable length combination that resonates at nearly that exact frequency. Get the tuning even slightly wrong, and the damper does very little useful work, moving out of sync with the building instead of against it. The mass itself also has to be enormous relative to the building's total mass to meaningfully absorb energy, which is why these systems often weigh hundreds of tons, sometimes over 1 million pounds. That's an enormous, expensive piece of steel or concrete that generates no revenue, occupies valuable floor area, and exists purely to move back and forth in a controlled way during the small percentage of days each year when wind speeds actually demand it. For most tall buildings, the damper system is never seen by anyone outside the engineering and maintenance teams, tucked away in a mechanical floor near the top. Taipei 101 made an unusual choice to put its damper on public display, turning a purely structural necessity into one of the building's most photographed features. But the engineering purpose is the same everywhere it's used. Without it, occupants near the top of a super tall building in a windy or seismically active region would spend uncomfortable amounts of time feeling the structure sway beneath them. And in the most extreme cases, resonant wind loading could stress the structure in ways engineers would rather not have to design around. The next time you're in a super tall building during a storm and it feels unexpectedly calm, there's a good chance a multi